Hey everyone, Dr. Green here for Intro to Software Engineering. Now to get into this class, the first question we really want to start working with, and the first question we really want to start asking is, what is software engineering? And also, why should we study it? So I think the first way to attack that question is really to break it down into its pieces, right? Software engineering, and there's some other things in there, right? Because we're also computer scientists. So we have to put all these together. So if we start looking at these pieces of the word, we'll start with our engineer or engineering. And we know that engineers, they learn what's true and they apply it to well understood and practical problems. We know this about engineers, whether they're civil engineers or nuclear engineers or chemical engineers, whatever type of engineer you are, aeronautical engineer, process engineer, they learn what's true and they learn how to apply it in the best possible way to build efficient and high quality systems that meet rigorous standards, right? This is what engineers do. They do lots of planning, they do lots of preparation, they do lots of evaluation and testing, and then they construct something that is awesome and amazing and safe, like buildings and planes and homes, okay? On the other hand, you have scientists who are involved really in acquiring knowledge and seeking truth, right? Scientists are normally found in labs and universities where they want to build up knowledge. They want to gain a deep understanding of some topic, how it works, why it works, what it does, all these kind of things. They use the scientific method to reveal truths about life and the universe. So these are really cool things, right? You'd think sort of like physicists, chemists in a lab, breaking everything down and building up these knowledge, seeking truth, and sharing it with the world. So you can have an engineer and a scientist, but we in this class are computer scientists, right? And we're concerned with computers. We're scientists concerned with computers, right? Which is a sort of weird thing. But we're scientists. We're seeking knowledge and truth about algorithms, languages, hardware, system software, applications, tools, all over the place, right? So we're concerned with how computer and information systems work, what truths hold to them, how you apply those, how you build them, all these kind of things. So you have an engineer, right, that learns and applies truth to build things. A scientist who is actually seeking out that truth and revealing it to the rest of us. Computer scientists who are worried about all this knowledge as it applies to computer systems. But you also have software engineers or software engineering, right? So software engineers are much more about creating high quality software in a systematic, controlled, and efficient manner. There is one really strange thing about software engineers, in my opinion, that separates them from other types of engineers. For an example, if you consider a civil engineer, they would build a building. They spend lots of time planning. They put out blueprints, all this kind of stuff. They source parts, they do testing, so that when they build a building, every pipe is in the right place, every toilet is in the right spot, all these kind of things. Okay? Now I want you to think about the last piece of software you wrote. Did you plan anything? Probably no. Why? Because as software engineers, as computer scientists, we have this really wonderful thing. We write code that sort of just lives in the ether in our computer somewhere. And when we want to build it, when we want to compile it, when we interpret it, we don't have to buy bricks and lay mortar and set down pipe and put the toilet and the sink in the right spot. We just press Command B and it builds in second at no cost to us. Right? This is the same, the equivalent of this for a civil engineer would be that instead of building blueprints and doing all this planning, they would simply walk into a site, start laying bricks, and if something didn't work, oh, that angle's off. They'd just take a sledgehammer, knock down the bricks, and then relay them in a better thing. Just think about it. This is what we actually do as software engineers. We try things and we're like, oh, that doesn't work. Let me debug it. Build, debug, build. And then we get really sick of it. It doesn't work at all. And we just build like 20 times because we expect something different will happen, which is insanity. But we do it. But this is one of those things that just separates software engineering, right? Building is fundamentally free. Building our product, going from our blueprints, our software, the code that we've written, to our working product, building that product is free, and it puts us in a very different category where we follow a very different process. Right? To put this in perspective, Fred Brooks said, a scientist builds to learn, an engineer learns to build. Okay, so that's a nice thing there. Concerning computer scientists, Steve McConnell would put us in a technological no man's land where you're scientists performing job functions that are normally done by engineers without engineering training. It's like having a physics PhD design electrical equipment for a commercial sale. The physicist knows what's going on, but they can't actually build the thing because they have no engineering training. And this is why software engineering exists, because we want to take the computer scientist getting a computer science degree, right, doing this kind of thing, and provide the engineering training to ensure that you can build high quality software projects. So let me ask you this. If that's all the case in point, what is it really? Like in practice, when you're on the job, when you're in the throw of things, what is software engineering really? Well, here's the classic cartoon to tell us what software engineering is, right? The customer explained that they wanted a tree swing with 3 seats. The project leader somehow understood that they wanted a tree swing that would swing whoever was on it straight into the trunk of the tree. Oh, I love that picture. The analyst designed it so you'd actually swing through the middle of this tree that was hanging balanced up somehow. The programmer didn't even manage to get the swing swinging. They just wrapped it around the trunk and left it there. The business consultant sold it as this nice lazy boy on the swing. There was no documentation. The only operations installed were 1 rope. The client was billed for a full roller coaster. The support was cut off at the trunk, and all the customer really needed was a tire swing. Right? So this is funny, but it demonstrates very clearly the problems in software engineering. It's communication between all the parties involved, all the stakeholders. And that communication is hard, and part of your job as a software engineer is helping people articulate not just what they want or what they think they want, but what they actually need. Another fun diagram of this is this Richard's Guide to Software Development, right? We had a cat designed, right? All these things. Somehow in beta testing, before beta testing, we had no back legs, and afterwards we had some back legs and no front legs. It was advertised as a tagger. The customer had no idea what they really wanted, but somehow we ended up with a cat with an elephant's nose with an arm coming out the back that we still managed to love anyways. Here's another answer, right? Name and describe the 5 key phases of software development. I love this. Denial, bargaining, anger, depression, and acceptance, right? Which are the 5 stages of grief. You will find, if you have not worked on a software project, that this process is very, very much like this. Here's another good example, right? Coding while learning at college while you're here, everything's buttoned up and nice. It's a perfectly painted, ordered Rubik's Cube. But in reality, and I can attest to this, that's what it looks like on the job. It's a Rubik's Cube where you sort of, maybe, mostly got it right, but you didn't actually get there by twisting it. You just painted the sides and all the colors overlap just a smidge. But what if this was something more, right? What if it wasn't just constructing or something funny? There's a lot of folks that think that software engineering, building software, is a creative endeavor, right? Fred Brooks says, the programmer, like the poet, works only slightly removed from pure thought stuff. He builds his castles in the air, from air, creating by exertion of the imagination. Our Sirkin Laylock, right? Every programmer is an author. I mean, isn't this a fun thing to think about? Like, writing code is actually a creative endeavor. There's different ways to do it. There's different looks and feels. But you are creating something new and something amazing, and you're creating it out there in the ether. You're making the computer do what you want, how you want, by manipulating these bits and bytes through this thing called code. That's a really cool thing, and I, to be quite honest, find this to be very true. In my experience, computer science students, software engineers, I find that folks in this discipline, they have all these other passions about reading and writing, about playing instruments, about painting pictures, in portraits, about writing poetry. They just have this deep creative side to them that I normally don't see in other engineering disciplines. And I think it's amazing because I think it correlates directly with the ability to write code, the ability to marry creativity with analytical thought. And I just think it's the coolest thing. And maybe if it's even more, right? Kent Beck, what if software wasn't made like we make a paper airplane, finish folding it and it flies away? What if instead we treated software more like a valuable, productive plant to be nurtured, pruned, harvested, fertilized, and watered? And you'll find out if you haven't worked on software before that this is what it's like. Software grows from version to version. It becomes almost like this living mass of entangled stuff that you constantly have to sort out and heal and work with. You know, what else is software engineering? Software engineering is also a lesson in trade-offs. You'll find out that when you build a project, you get to pick two things between cost, time, and quality. We can either manage the cost in a reasonable amount of time, but it's going to cut the quality. You can have low cost and low quality, you know, and quick time, right? These are all trade-offs that go back and forth, but they're going to be important to make. There's also the more formal definition. What is software engineering? The application of a systematic, disciplined, quantifiable approach to the development, operation, and maintenance of software. That is the application of engineering to software and the study of those approaches. So there's a very formal definition we can wrap around it as well. So that's really what software engineering is, but then the question becomes, why study it? And the fundamental reason I will give you to study software engineering is very simple, and it is failure. You can't spell failure without you, because most likely you caused the failure. Software engineering has a rich history of terrible failures that we are trying to avoid. That's the whole reason we have these software development processes, right? So I'll give you 3 examples. First, the virtual case file project. FBI project ran back in time, cost millions and millions of dollars. Hundreds of thousands of lines of code written. They worked on it, they worked on it, they worked on it, and what happened? Oh, $170 million later, they just completely abandoned it because it couldn't work. Failure. The Ariane project was a European rocket that was built. It cost $7 billion. The software was written incorrectly, so when it left the launch pad, it veered to the side and exploded. And it was a software error, right? It was a data conversion error. It's only a $7 billion mistake. And there's also the classic story of the radiation overdose. A software engineer that didn't test his code properly, used the wrong data type, a short instead of an int. And what happened? Well, data was stored in the short. It was too large for the short, so it overflowed, and somebody ended up receiving a lethal dose of radiation. So these are all terrible failures. We don't want these to happen, and that's one of the goals in this class. You study software engineering to avoid failures. You can click on this link and go see many, many other failures of software engineering to be discussed. So that's where I want to start. I want you to think about these 2 questions deeply, right? What is software engineering and why bother to study it? If you feel like you can't think about them deeply now, keep them in the back of your mind the rest of the semester as we dig into the software engineering processes, why we study them, and how we apply them.